Now let us quickly review what we have seen in the last class. We have seen an introduction to radiation in the last class. So this radiation, we have seen governing law. That governing law is Stephen Boltzmann law we have seen. And the physical mechanism of heat transfer is electromagnetic waves carry this radiation heat transfer. Also, we have seen that the Stephen Boltzmann law, according to Stephen Boltzmann law, Q is proportional to A and Q is proportional to T to the power of 4. Combining these two, you will get this equation here with the proportionality constant being sigma, which is Stephen Boltzmann constant you have seen. And if you take net effect for two bodies, one the emitting body, the other the receiving body, the equation will become like this. If you consider the effect of emissivity also, that also will be multiplied here. And then Q will be the rate of heat transfer by radiation. And this will be measured in watts, which is nothing but joule per second you have seen. And the area here is the area of a emitting body. Here it is an emitting body area and it is measured in meter square. Emissivity is a constant we have seen. It doesn't have any unit and it will vary between 0 to 1. And emissivity is equal to 1 for a black body and for a gray body it is less than 1. So this is what we have seen. And then we have also seen that the T1 will be the temperature of the emitting body and T2 will be the temperature of receiving body. Sigma is a Stephen Boltzmann constant, which value is 5678 is the code to remember it, which is 5.67 into 10 to the power of minus 8 watt per meter square Kelvin power 4. This is the thing we have seen. And regarding these temperatures, it should be in Kelvin and it is not in degrees centigrade. This is what we have seen in the last class. And we have solved a problem where we have considered a person standing in a room and there is a room. This is a body 1. This is body 2. Between these two persons, these two bodies, what is the radiation heat transfer you have calculated in winter and summer, and you have found out that the winter value is very high compared to your summer value, and this is the reason why the person feels chilling, and this is how the human comfort is defined by your radiation, right? So also we have seen how the radiation is helping you build this evacuated tube solar water heater, and this evacuated tube solar water heater, how it is blocking your heat transfer by conduction and convection, because the vacuum is taken in this part. Here you have vacuum. This vacuum, what it will do is it will allow the heat transfer to happen. Radiation heat transfer can happen even in vacuum. That's we have seen. And the thermosiphon effect will be helping you carry the water from bottom to the top. Okay. And then I have given you assignment, and yeah, I have seen that most of you have submitted it. Yeah, I'll speak about this at the end. So let's move on to our next thing. Next thing that we should see here is two basic things. Let us see here, two simple definitions we will see now. After seeing these two definitions, we will go to the derivation of 3D conduction equation. So in this class, basically what we will do is we will look at the 3D conduction equation. Before that, let us look at two basic definitions that you should learn. They're like, first one is heat flux. You must know what is heat flux. Heat flux is shown with small q, which is actually q by A, and it is measured in watt per meter square. So it is nothing but heat transfer per unit area. Heat transfer taken upon unit area is called as heat flux. Okay. Your area may be very small sometimes. Your area may be very big sometimes. But to neutralize the effect of area, heat flux is taken. However big your heat transfer area can be, that area, if you take it per unit, no, if you divide it with Q, sorry, if the Q is divided with area, then that will be giving you the heat flux. So the small q is giving you the heat flux value. It is measured in watt per meter square. And then one more thing is rate of internal heat generation. Rate of internal heat generation. So generally, I told you in the beginning of this lectures that the heat transfer will happen because of the temperature difference. Okay, the driving force for heat transfer is temperature difference. Other than temperature difference, other than temperature difference, if heat is added or removed from the system or your control volume, system means here control volume, then that heat is called as internal heat generation. And this internal heat generation is shown with Q gem. See, how can this happen? If there is no temperature difference, how can the heat transfer will come? Okay. So see, other than temperature difference, heat transfer can come by other means like your chemical reaction can happen and nuclear reaction can happen. So and so. So many things like this can happen. Other than temperature difference, anything can happen to give you heat. Okay. So these things will give you something called as internal heat generation. And this internal heat generation is taken as Q upon volume. See, in the first one, I have told you this is a Q upon area. And here, Q upon volume is taken, and the unit for this one is watt per meter cube. Okay. So these are all the things, two things that we should have in mind while we look into various heat transfer problems. So uh, we will move on to the next thing, that is your 3D conduction equation. Okay. So in your 3D conduction equation, this is what I have taken here. There is a cube that you can see, it's a cuboid. And this cuboid, what I've taken is this is taken from a huge heat transfer space. I have taken a small thing. And in every conduction, sorry, it is not conduction, every differentiation thing. Okay, you will do differentiation. How you do differentiation? You take a small thing and you apply it to the whole body. Okay, you take a small thing and you apply it to the whole body. That's how differentiation will happen. The integration will be reverse of it. You will take the whole thing and you will consider it for a small body. So here I have considered infinitesimally small element. So I should put heading here. The heading will be like 3D conduction equation. And this will also be said like generalized conduction equation. And today we are going to solve this in Cartesian coordinate system. Cartesian coordinate system. Basically, you have to solve this in three systems. That is Cartesian, meaning rectangular. This is also called as a rectangular system. And the other thing is your polar coordinate, that is your cylindrical system. The other thing is spherical. So three derivations you will have. And one of the important thing I should tell you regarding this derivation is that, see, this is what the question you are going to get in your examination. The long answer question will be this particular thing only. Okay, most of the times you will get this equation, this derivation only. Either it is in Cartesian coordinates, polar, or cylindrical coordinates. Okay, uh, these three things will be there, same derivation, only coordinate system will change. Okay, out of these three, any one question will come pakka. Okay, most of the times this is the question that you will get from unit 1, because this is the only potential question that you have for long answer question in unit 1. There are no other questions in unit 1 to give you. So most of the times this is a question that you're going to get in your examinations from unit 1. So if you learn this, okay, you are done with your examination for first one, first unit. So learn this properly, listen to it. It is very easy. Okay, if you listen to this lecture carefully, you will have clarity, and now itself you can learn it. So what I've considered here is, in a huge heat transfer place space, I have taken a small element. Okay, even though I have shown it as a big element here, it is actually a small element with small dimensions. Now I will consider this as my x-axis, this as my y-axis, this as my z-axis. So this distance will be this distance. Let me take this double headed arrow. And this distance, let me take it as dz, parallel to z axis. So I have kept it as dz. Then this distance, let me call this as dx. And now this distance, yeah, this distance will be your dy. It is parallel to y, so this will be dy. So these are the dimensions of your space. So the volume of this space, I'll be writing with a hash here, so that I am representing volume and velocity differently. Generally, volume is given a dash here. Okay, so this volume will be equal to dx into dy into dz. Okay, xyz will be your volume measured in meters square. Now you are done with your dimensions. Next thing is, you have to take this space. Okay, the space that is there in your yz plane, and on that plane perpendicular to it, a heat is entering in x direction. This is x direction. So at this space now in xy plane, sorry, yz plane, heat transfer qx is entering. And on this plane, on the other side of this plane, that is yz plane, the other side of the cube, a heat is coming out, and that heat is Qx plus dx. What is this dx? This dx is accounting for the infinitesimally small change that has happened over this thickness, okay, this distance. So this will be Qx and this will be Qx plus dx. Now I will take it in y direction. And in y direction, the thing will be entering in your, Mohan, please switch off your video. Uh, the heat transfer will be entering at the y, sorry, xz plane. So this is y that is entering in the yz plane as qy, and it is leaving on the other side of the plane as q. Maybe you can show it. Qy plus dy. And now in this direction, at this plane, that is your xy plane, qz is entering. On the other side of it, qz plus dz is coming out. Okay, so this is very simple. You have taken a cube here, you have given it a dimension, you are giving it the heat transfer that is entering and leaving. Heat transfer that is entering on one side and leaving on the other side. Entering is x, leaving is plus dx. Okay, same is repeated for your y and z also. Y is entering, y plus dy is coming out. Z is entering and Z plus DZ is coming out. So you are accounting for infinitesimally small change that is happening in your control volume. All right. So this is what you have taken. Now, if I have to take this QX, what is the formula for your QX according to your Fourier's law of heat conduction? Somebody say it. It is minus
K dx dt by dx.
K into dt by dx. Good. So this k I should take in x direction. Okay, because I'm taking it in x direction, I'll be taking it as kx. So minus kx into what is the area here? It is d
dy
this one.
dx.
This is dz, so this is dy. So it is dy into dz. See what we told, area in this particular Fourier's law of heat conduction is area perpendicular to the direction of heat transfer. Here the area perpendicular to the QX is this area, this this dz and this dy. This dy and this dz, if you take, that will be square or rectangle, and perpendicular to this, this is going. So the same dy into dz I have taken into dt by dx will be your qx. Okay, let's keep this qx aside. And now I want to get qx plus dx. How do I get qx plus dx? How to account for the infinitesimally small change that is going to happen in any control volume? Somebody please tell me how to account for the infinitesimally small change that is happening in a control volume. How do you account for it?
Qx plus d by dx of qx.
How did you get that?
Well, it's small, so I integrated. Sorry, differentiated the whole thing.
It's small, it's differentiated. Huh? Mhm. See, it is based on your Taylor series expansion. Okay, Taylor series expansion you will see in mathematics. This will help you in accounting for the infinitesimally small change that happens in a control volume. Okay, so if you have to take this according to Taylor series expansion, how it will be qx plus dou by dou x of qx into dx plus higher order term. You will get dou square by dou x square into q into dx whole square, and so on. So many terms you will get. So those we will call it as higher order terms. And these higher order terms are so small, so the effect of it will be neglected. So you need not consider them here. So effect of these things is neglected. So till here you will take. So Taylor series expansion is telling you that you should take it like this. So what it will be like? So q x plus dx is equal to qx plus dou by dou x of qx into dx. So this is what you will take for qx plus dx. Now, what I want to do is, I want to consider net heat transfer that is happening in three directions. And how do I take that equation? To account for that, what I'm doing is, I will take rate of heat transfer by conduction. So overall heat transfer I am taking here. And in that overall heat transfer, conduction will be one part. And then along with conduction, you will have rate of internal heat generation. Rate of internal heat generation. I told you just now that rate of internal heat generation is nothing but the heat transfer that is happening in a system because of the source that is other than temperature difference. So other than temperature difference, some heat is coming into the system or going away from the system, that we call it as rate of internal heat generation. So apart from conduction, this can also be there. Okay, these two put together will give you something called as rate of heat stored in your system. Okay, rate of heat stored in your control valve. So this is very important equation here. Simply put, it is conduction. Okay, it is conduction, and then it is internal heat generation, rate of internal heat generation. Actually, it is heat stored here. So these are the three terms which you should have in mind. It is conduction in the first place. It is internal heat generation in the second place. The third place is heat stored. So whatever the heat that is entering into the system and leaving into the system, you will take by this one. So let me write it here. This is Q by conduction plus Q. This is generally shown with small q. So I should say it is Q gen is equal to Q stored in the system. So how do I take for net rate of heat transfer by conduction? Okay. Now, if I have to take the net rate, it is Q conduction is equal to Q x plus dx. Sorry, it's not Qx plus dx. Qx minus Qx plus dx will give you net rate of heat transfer in y direction. Okay. This is x direction thing. Okay. Same way, if you have to take it for y direction, it is q y minus q y plus dy. And z1 also, if I take q z minus q z plus dz. Okay. Right. So this will be your q conduction. Next, how do I take q gen here? How do I take q stored here? Okay. These things we should see here. See, if I have to take q gen here, no, the q gen will be has to be taken like q gen per unit volume. Okay. Why should I take it? Why should I take it like this? Because see, this is measured in watts. You have said that here. This equation you have taken in this equation, what is the unit of qx? It is watts. Okay. So here also it will be in watts. So when you are adding something to something, both should be in same unit. Like you should add a rupee with rupee and you should add dollar with a dollar. You should not add a dollar with rupee. Okay, you should not add two different units. Same way, here also, this is in watts. So what I want to do is I want to convert this one also into watts. So the numerator is in watt per meter cube. And then if I take it as this volume, so this volume should not be divided actually. This should be multiplied. Okay. This I should erase. So this is Q gen into dV I should take. It is not Q gen by dV, it is Q gen into dV. So that the unit will become watt per meter cube into meter cube. So this meter cube will get cancelled. What you get is watts. So now this Q gen should be taken. This Q gen should be taken in this form, dV, Q gen into dV, small q gen into dV. That's how you will take. Now somebody tell me how to take Q stored inside the system. How to take it? Somebody please tell me. This I have already told you actually. Can somebody tell it? How to take Q stored? How do you quantify the stored heat stored in the system?
MCDT.
EMCP Yeah, very good. CP, whenever I say CP, it is heat stored in the system. MCP Okay, MCP Good. Now, what is the unit of MCP here? What is the unit of MCP? If I take M, it is kg. What is the unit for CP? Somebody tell it. CP, what is the unit? CP, what is the unit? Someone is saying is
Kilojoule per
joule
kg
per kg
Kelvin.
Kelvin. And dt will be having unit Kelvin. So Kelvin cancel, kg cancel. So what you get here is joule. But this Q is in watts. So on the other side of the equation, you should have the same unit. Here also the unit should be in watts. Here the unit is in watt per meter cube. And here the unit is in joule. So what you have to do is you have to convert this watt per meter cube into watt and joule into watt. So how to convert this joule into watt? For converting that, what I'm doing is I'm taking it like mCp dt by dt. So can I take this dt over here? That is, can I change? Can I take Can I take this time or mass? No, you cannot take it because the mass is fixed and mass is not changing. Can I take with respect to Cp? No, you cannot take with respect to Cp. The Cp is also more or less the same. Something happened. Give me a minute. Now you can see it. Yeah. So I can take it with respect to only I can take with respect to only temperature because the temperature is the only thing that is changing here. Now, to take that, what I have taken is I have taken it only with respect to the temperature. So this will be on the other side of the equation. Now, if I take this qx plus dx and this difference, no, how to take that also we should see. So for that, what we will do is qx minus qx plus dx. If I write, this will be equal to qx minus qx plus dx is qx plus dou by dou x of qx into dx. So this qx will get cancelled. This will give you minus dou by dou x of qx into dx, what you will get. So also you know that dou by dou x of qx is nothing but minus k into d. It's not dx, it is dy into dz, area perpendicular to the direction of heat transfer into dt by dx into dx. This is what you will have. So this minus into minus will be plus. This will be equal to k. This is actually kx. We will take kx outside. Dx, dy, dz are also not changing. You can take all of them outside. Dx into dy into dz will be taken outside. And you take dou by dou x of dou t by dou x will give you dou square t by dou x square. So this is actually taken in partial differentiation, meaning that you are considering only the change in x direction. You are not you are not considering the change in y and z direction. That's what the meaning of partial differential equation. Partial differential means you are considering only that particular variable. Other variables you are not considering. So that's what you have taken here, dou. So that's what partial differentiation is. So this is what your qx minus qx plus dx value. So this will be equal to your kx into dv into dou square t by dou x square is your qx minus qx plus dx. Also, similarly, if you do for qy minus qy plus dy, this will also be like similarly ky into dv into dou square t by dou y square. In place of x, you got y. In place of x, you got y. That's the only difference. You can do it for yourself again, but you will get the same thing. Q z plus dz will be equal to kz into dv into dou square t by dou z square. So this is what you have. So this is your equation here. What is your equation? This is your equation. This is your equation basically. And into this equation, you got so many things. You got what is Q conduction using these three here. Okay. And you got Q gen and Q stored. Let us substitute all the equations into this equation. Okay. Let's call this as 1 and this as 2, this as 3, and then 3, 4, 5, 6. So what I will do is substitute 2 to 6 in equation 1. If I substitute, the equation will be like the kx is there. So what I will do is dv is common. I will take dv as common, put the dv outside, kx into dou square t by dou x square plus ky into dou square t by dou y square plus kz into dou square t by dou square t by dou z square plus what I should take here q gen into dv is the value according to your equation number 2. Now, equation number 3 will give you this value as m cp into dt by d. See, what is the small t here? Small t is your time. Okay. Capital T is your temperature. With respect to time, I have taken here because this will become joule per second, giving you watt. Okay, so that is the reason why I have taken it like to convert this. What I have taken joule per second will become watt. Okay, so that's the reason why I have taken with respect to temperature, with respect to time here. Small t being time, small t being a time. Right. Mm. Now, in this equation, okay, if I consider if kx is equal to ky is equal to kz, that is thermal conductivity in all directions is equal. If that is the case now, what I can do is I can take k as common. So what I get is dv into k is dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus q gen into dv is equal to mcp dt by dt. Now, you can see that dv is common on this side. So k is also common. I will take this onto the other side. Then what you get is dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus q gen by k is equal to M into Cp by, here you will get K into dV you will get. So I will write dV into K, dV into K into dt by d small t. So this is how your equation will be. And in this equation, what is mass by volume? Mass by volume is nothing but your density. Rho Cp by K into dt by dt you will get on this side. So can somebody tell me what is this K? What is by rho Cp by K? Can you remember what is K by rho Cp? Hmm? Did you remember what is K by rho Cp? Can somebody tell me what is K by rho Cp? Hmm?
Thermal diffusivity.
Yes, it is thermal diffusivity. You have represented with alpha. So here it is reverse. So we will write it as 1 by alpha. So it is dt by dt. You will get here this side. You will get dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus q gen by k. This is your final equation. This is your 3D conduction equation, which is representing your physical heat transfer by conduction. So this, whatever the physical problem is there is represented by this equation. There will be some modifications to this one. Okay. The modifications are like, if the case is steady, if it is a steady heat transfer case, no, dt by is 0. Okay. That is rate of rate of temperature change with respect to time will be 0. That we call it as steady state. Okay. So then this will become 0. Then your equation will be like del square t. This whole thing is represented with del square t plus q gen by k equal to 0. This is one assumption. If the given case is steady and Qgen is also equal to 0, then you have something called as del square t is equal to 0. So this equation is a kind of Laplacian. You must have studied what is a Laplacian in your mathematics course. And this is your Poisson's equation. To a Laplacian, you have something added that will be your Poisson's equation. Okay, these things you should keep in mind. So with this, I'll close it for today. There are some more discussions to be taken up in this particular thing. Those things I'll be dealing in the next class. So this is all the equation. Now, if you have any doubts, please ask me, or you can leave the class. I
Sir,
hope
why
most
should
of you
we
have
take only plus
posted
two?
the attendance. Pawan, please wait. See, most of you have posted the attendance, I believe. If you have posted the attendance, you can leave. Yeah.
Sir, why should we only take qx plus dx, sir? Plus or minus? Why shouldn't we take plus or minus, sir? Heat can be increased or decreased, no, sir.
Which one you are speaking about? This one now.
Conduction equation, 3D conduction equation.
Here, why did I take plus? Why shouldn't I take minus? Is that your question?
Yes, sir.
See, I'm taking it. What I'm doing is I am taking positive in this direction. Okay, in this direction, positive. All three directions, I am taking positive. That's why I'm taking positive here. If you take minus here, take minus in all three things, you will get the same thing. Your thing will not change. Whether you take plus or minus here doesn't affect it at all. Okay, you take minus on all three sides, you'll get the same expression again. It doesn't vary. You got it?
Yes, sir.
You do it for yourself, you'll understand. What?
So
Because I'm not interested
Just
in whether
one
it is
small
positive or negative. I am interested in net. I am interested in the net heat transfer. Okay. Yeah. One more question somebody is asking.
control to
Sai
steady
Krishna,
equation.
come again.
Last two study equations, sir.
Yeah. Hmm. Yes, tell me. Sai Krishna, you have asked something.
No, sir. I didn't wrote, sir. So to write, I asked for the shows.
Okay, okay. Right.
Sir,
Hmm.
why are considering specific heat at constant pressure, sir?
Specific heat?
At constant pressure. CP you wrote na, sir.
Why don't I consider CV? That's your question, huh?
Yes, sir.
Tell me why it's so. See, CP is equal to CV for all the things. Let me complete this. See, for solids, no, for liquids and solids, CP is almost equal to CV. Whether you consider it or not doesn't matter. Cp minus Cv is equal to R, where R is your universal gas constant. Cp minus Cv will have a huge value or a significant value only for gases. That's why you have something called as universal gas constant. Okay, for liquids and solids, the Cp and Cv value will be almost same. Okay, and the R value will be zero for liquids and solids. This is the reason. You got it?
Yes, sir. Okay,
Okay.
thank you.